All right, good morning, good afternoon, or good evening, class. This is Mr. Manta, and you are now watching the second video, our second of our online video lessons for science. This lesson is for Wednesday, March, 18th? So hopefully that's today's date. And we're going to be talking all about lasers. I'm very excited for this lesson. I'm kind of introducing, for the first time today, really digging into deep about what light is, and we're using lasers to do so. Before we jump into that, I do want to make a couple quick announcements, 1 and 2. First off, announcement 1. Several students still have not completed their Unit 5 quiz on energy, which was supposed to be completed on Monday. Now, I'm pushing back the due date so that today is your last day to do this quiz. If you haven't done it yet, please close this lesson, stop watching the video, and go do the quiz before coming back to this video. If it's not completed today, your quiz will go in the gradebook as a 0. I don't think you want that. Now, most of you have already completed the quiz. A few of you are probably asking, what quiz on earth is Mr. Manta talking about? Well, let me show you if I find the right tab. If you come to our Google Classroom page right here, you'll see today's Wednesday, yesterday was Tuesday. You need to go all the way down to Monday. On Monday, you're supposed to have completed this Unit 5 energy quiz. I scheduled that for Monday before we knew we were shifting to online lessons so soon. But what you have to do is come down to Monday, open up Unit 5 Energy Quiz, click this link, and go ahead and complete that quiz. If you haven't done so, today is your last day to do that quiz before it's counted as a 0. I highly recommend you do it. Second announcement has to do with money. Not real money, of course, but scholar dollars. You probably could have guessed that. That is that, for one, you should probably know this already, but you are earning and losing scholar dollars each day for whether you complete your science work, which gives you plus 10 every day, or don't complete it, which is minus 10. What's special for today, if you want to earn some extra dollars, you are welcome to take a picture of the notes you took during today's lesson and upload that picture at the end of today's classwork questions. So while this video is playing, you should be taking notes in your science notebook. And if I come over here to Wednesday, March 18th, to today's classwork assignment, which you should also have open to complete during or after the video, this one, I'm going to have question 1, question 2, and then right down here it says optional, upload a picture of your notes here to receive bonus scholar dollars for today's work. If you have the capacity to take a picture and upload it, then go ahead and upload your notes from your science notebook here. I'm going to be looking through those to see who is taking the most beautiful, informative notes, and go ahead and probably use that person as an example, like show their notes as an example for everybody else. But anyone who uploads their notes and has them completed the right way will be earning scholar dollars for it. So, highly recommend you do that. Alright, now actually getting into today's lesson. The question we're kind of starting with today is really simple. What is a laser? Now, we have some examples of places that we've probably seen a laser somewhere in your life before. The most common of those, you may or may not have ever seen someone use one of these little laser pens or laser pointers. You can buy them on the internet. They're pretty cheap. They come in all different colors, green, purple, red, blue, all these different colors. I had one of these growing up. I always really enjoyed playing with it. You may have seen like a spy movie or something like that, where somebody has to sneak through a whole field of lasers in order to like sneak by some secret chamber and go rob a bank or something. And they use the lasers so that if the person touches any of the lasers, an alarm goes off. You may or may not know, actually, that there's lasers all around you in all kinds of different machines and pieces of technology that we use. For example, if you're using a computer mouse right now, one way that a lot of computer mice work is that they have a little laser down in the bottom of them that's kind of tracking the mouse pad underneath it, so that when you move the mouse around, that's how it knows where it's going and like where to move the mouse on the screen. And yeah, this is my favorite example. Some of you, maybe not so many, it's Mr. Mantra's favorite example, maybe not know at sometimes concerts or rock and roll shows, people will use lasers to put on a laser light show that accompanies the music. And you can watch them all day. They're very mesmerizing and pretty and fun to watch. But we're not going to be going to any laser light shows today. We're really examining the question, well, what is a laser? We're going to start with a quick fun fact. First of all, you may or may not have known this. The word laser actually started as an acronym, L-A-S-E-R. What that stood for is light amplification by stimulated emission of radiation. Now, you don't have to know all those words. It's a lot of big fancy science words. I'm not going to ask you to remember all of them. It's just fun to know that laser is one of these words that actually started as an acronym. And then people have said laser so many times they got sick of typing capital L-A-S and just changed it to the word laser. Now we all use it. This is actually pretty common. Another word that's kind of like this that you might have heard of is scuba. Like this person right here, they are a scuba diver using their scuba tank and their scuba gear to breathe underwater. Scuba is also an acronym. It stands for Self-Contained Underwater Breathing Apparatus. But people got sick of saying that every single time, and so they started abbreviating it just to scuba. Laser is the same idea. We don't want to say light amplification by stimulator emission radiation every time. We just want to say laser. What we need to know, though, this is very important for today, is that a laser is the simplest, or I would almost say purest, form of light. It is a kind of light, and compared to all the other kinds, it's very simple and pure and basic. It's just a simple little laser beam. You might be wondering, Mr. Manta, why are we already jumping into a lesson about lasers? Why don't we learn about just like normal light first of all? Because lasers seem really advanced. Well, in reality, this, just a normal lamp or a light bulb in your house, is more difficult to understand than this. We're going to start with lasers because they are simple, and then we will work our way back towards what we call visible light, or just the normal light that comes from the sun or a lamp in your house or something like that. We're starting here today. Oh, we're going to start here. There we go. So, here's the question. If you could zoom in super close on a laser beam, what would you see? We're finally going to get a glimpse inside of the laser beam and figure out what it really is, what's going on. Well, let's zoom in. If we look in super duper close, what we would find is something like this. That laser beam, what it's actually made up of, if you could zoom in on it and slow down time, is a whole bunch of individual waves. If you could look closely enough at light, you would see that it is waving. It is all these waves kind of progressing from one side to the other in the direction that the laser is pointing. It's a whole bundle of these individual waves that we're going to call light waves. This is what laser beams are made of. Really, this is what all light is made of. But again, we're starting today just with lasers. So, that laser beam that you see really is composed of a whole bunch of individual moving waves. This is a big idea we're going to be talking about for the next several days. Light is made of waves. Key point. Light is made of waves. That should tell you, make it very clear that that's something that you really need to have written down in your notebook if you haven't already. Now, we're going to look at a diagram of a light wave, and there's going to be a few different parts. We're going to zoom in on just one single wave to try to make it simple, and name a few different characteristics of a wave. So here I have a wave. I really suggest that you draw one in your notebooks that looks really similar to this. First of all, make sure that it's like, don't make a super complicated wave where it's going up and down a million different times. That's bad. Don't do that. Have one that goes maybe up and down just 1, 2, or 3 different times, and is high enough that, because you're going to need to label a whole bunch of different stuff on here in just a second. So first of all, draw a wave kind of like this one in your science notebook. Second of all, one thing that we might notice, that you should know looking at a wave like this. Oh, other thing you want to add to your diagram. Go ahead and put a dashed line kind of running down the middle, because we're going to use that as kind of as a point of reference to look at some different features of a light wave. Alright, now here we go. One thing that's important to know is that there's different names for different parts of a light wave. These parts up here, where it goes to the very highest point on the wave, are known as peaks or crests. You can use either one of those words. You will see both of those words used. Again, that's because there are these 3 really high points up on top of the wave. You can also look at the opposite, these points down here, the bottom parts, and we'll find out that those are called valleys or troughs. That word T-R-O-U-G-H, that's pronounced trough. That means it's a low point in the wave, the opposite of the peaks and crests, which are the high points in the waves. Now, 2 more things that are really key to know. There's ways that we can measure the characteristics of different waves. One of them is called amplitude. And amplitude measures the height of a wave, going from this middle line that goes straight down the middle of the wave, all the way to the very top of the peaks or crests. All 3 of these peaks are going to always, like every peak in a light wave is going to be equally tall every single time. And the amplitude is the measurement from the middle line, right here, up to the very top of the peak. So if you could zoom in close enough, you'd be able to measure this and say that, oh, maybe it's like 4 nanometers or something like that, the same way that you measure, I don't know, the length and the width of a rectangle, something like that. This thing right here, amplitude. You can measure amplitude going from the midline to a peak, or from the midline to a trough. It's always going to be the same length, the same distance, both ways, on both sides. So that's amplitude. The second way that you can measure and describe a wave is called wavelength. The wavelength is the distance from one peak, or one crest, whatever you want to call it, to the next peak on that wave. That distance from here, straight through and across to here. That's going to be the exact same distance every time it waves up and down. So that's going to be the same distance as from here to here as well. And it's the same distance on top and bottom of the wave. So this distance right here is going to be the same distance from this trough to this trough. You can measure wavelength either way. Scientists do measure wavelength both ways all the time. And that is called the wavelength. That's a term we're going to be using a lot, so remember it now. You should have a diagram at this point in your notes that looks just like this diagram that I have here, including your vocabulary words labeling the peaks, the valleys, the amplitude, and the wavelength. I want to show you quickly just some, oh yeah, and stamp it as important because we're going to keep on coming back to this and these ideas. I want to show you just a few more examples of other diagrams. These I just found on the internet, just to show you that they're all labeling the same basic ideas, the key things that you need to know in a wave. They just use different words, so they call it a peak over here and a crest over here, but either way it's the same thing, the top of the wave. They are all showing the amplitude of their waves, amplitude, amplitude, and they're all also showing the wavelength of a wave. That means from peak to peak or from trough to trough. Amplitude, wavelength, two different ideas. Alright, this is the point where we're getting to a couple classwork questions. So either write down your answers to these questions in your notes, or have a separate tab open showing, here I'll show you guys, showing the classwork questions like I'm looking at right here. Give me your answers, type them directly into question 1 and question 2. Here are the questions. Number 1, take a look at this diagram that I've got here and tell me what each of these 4 points I've labeled A, B, C, and D are. So you can type your answer out with words. Tell me A is this, B is this, whatever you think they are. Pause the video, do that now. And alright, hopefully you've unpaused, coming back to the video. I'm going to show you the answers. Don't change your answers in the classwork, it's fine, that's not being graded for accuracy. But we should know that in this diagram, A is a trough or a valley, the lowest part of the wave. B is the wavelength, that's the distance from one peak to another peak. C right here is the amplitude, that's kind of like the height of the wave measured from the baseline up to the peak, or from the baseline down to the trough. So if I put C here, that would still be true. And D is a peak or a crest. Hopefully you got all those terms right. We're going to be using those terms a lot, and I want you to know what I'm talking about when I say the wavelength is this, or the amplitude is that. Classwork question number 2. Alright, again, you're typing either writing in your notebook or typing this directly into your classwork webpage. Here's the question. You're making a prediction this time. All light, including lasers, is made of light waves, like this one. So that's the same. But we also know that lasers can be different colors. What do you think determines the color of a laser? Thinking about this light wave diagram that we just went over, there's something that can be different about different lasers that's based on their color that also is different when you zoom in really close and look at their different features. Take a guess, go type your prediction, and pause the video now. Alright, go ahead. Hopefully you're bringing the video back again. We're going to go through the answer to this because this is a very major idea for today. Why do different lasers become different colors? Well, here we go. Big key point. The color of a laser depends on its wavelength. You know what wavelength means now, so that should make sense to you. You're going to see diagrams like this all the time in science moving forward. What you're seeing here is that different colors of light, from red from at the bottom all the way up to violet at the top, have different wavelengths. The waves, in other words, are kind of more, bunched closely together or really stretched out, and that affects what color of light we end up seeing. So when the waves are really bundled closely together like this, we see violet light or purple, and when they're really stretched out like this, we see red light. No matter what, the amplitude of the wave is not changing. So this wave is it's no taller or shorter than this wave down here. It's not about the amplitude, again, it's about the wavelength, how bunched together, how spread out the different waves are. So this one, it's showing you that their wavelength is 400 nanometers from peak to peak, whereas the red light down here is 665 nanometers from peak to peak. That is why violet light looks violet and red light looks red, and all the different colors in between look the color that they do. So green is somewhere in the middle. It's 550 nanometers in wavelength. Wavelength affects color. Violet has the shortest wavelength, and red has the longest wavelength. If you were writing this in your notes, maybe don't need to copy this whole diagram, but maybe give us an example just of violet light and red light, because those are kind of the two extremes, and then knowing that everything else falls in between. So, turning back to our laser pointer question, if we lined up a red, yellow, blue, and purple laser pointer next to each other, and then zoomed in again, what would we see? Well, let's line them up. We got our red, yellow, our blue, our purple, and we're going to see what their light looks like. When we zoom in super close, it looks like this. You'll notice that we have separate waves going on for each laser. So we have our red light up here, our yellow, our blue, and our purple laser beams. And each of them have these waves going on that are kind of the same basic idea, but they're different in terms of how stretched out their wavelength is. So red has these long waves that kind of go up and down much more slowly, whereas the violet light has these really short little waves that go up and down and up and down and up and down the whole time. That's what makes this one purple and this one red. Yellow is somewhere in between, blue is a little bit closer to violet, but it's still not quite as short of a wavelength as the violet light down here. Alright, one last thing we also need to know for today, in order to complete your exit ticket, in order to be ready for whenever it is that we eventually have a quiz or a test. Remember the name of this unit? We call this unit, Unit 5, energy and light. Well, we talked about energy, and we've talked about light, but we haven't really connected them so far, other than to say that light is one form of energy, but it's energy and light. Well, here is the connection, and the reason why we're putting those two ideas into one unit. Now, the third and final key point for today. The amount of energy that light has depends on the wavelength. Just like color depends on wavelength, energy also depends on wavelength. And here's how it works. Violet light, up here at the top with the shortest wavelength, has the most energy, compared to red light, down here at the bottom, has the least energy. In other words, the shorter your wavelength is, the more energy you have. So light with really short wavelength is super packed with energy. On the other hand, the longer your wavelength is, the less energy you have. So red light doesn't have a lot of energy because its wavelength is too wide. Violet light has a lot of energy because it has this short little wavelength. And again, all the other colors are somewhere in between. So violet light has more energy than indigo, which has more energy than blue, which has more energy than green, which has more energy than yellow, all the way down to red, which has the least amount of energy overall. I want to make a connection here. This Mr. Manta gets really jazzed about because this connects all the way back to something that we learned in our astronomy unit, and I didn't even realize that these things would connect. It makes me so happy to see how they are. Well, you hopefully remember this from astronomy. When we were talking about stars, we said that different colors of stars have different stars, in other words, have different colors, and their color tells you something about their temperature. So blue stars are the hottest, and red stars are the least hot, and all the other stars are in between. Well, I'm going to take that diagram and just put it over there to the side real quick, and put that right next to a diagram of the energy level of various wavelengths of light, and what you'll see is basically the same pattern. Blue stars are the hottest, and blue light has a lot of energy. Not the most energy, I guess. Violet would have more, so you could have a violet line down here with even more energy. But, point being, blue stars are the hottest, and of these colors that we're seeing here, blue light has the most energy. Red stars are the least hot, and of all the colors, red light has the least energy. It's the same basic pattern. Orange stars are like medium cool, and orange light has like a fairly small amount of energy. Yellow stars are right in the middle, and we see yellow light right. The only one that doesn't really line up is that we have white stars here, but we have green light here. I'm not sure why we don't have green stars. That'd be pretty cool. Maybe someone should write to the scientists and tell them to go try to find a green star. But the basic idea is the same. It all connects. The same basic order of colors that we have, determining the color of a star and its temperature, is the same basic order of colors we have when we're looking at light and how much energy light has. If it's hot, it has a whole lot of energy. Alright, folks, that is all for today. You can go ahead and close out the video. We're going to wrap up right now and go and do your exit ticket. Again, you should be doing your exit ticket just from memory, maybe using your notes, but not going back to watch the video again. And last couple things I want to mention. For one, you have science homework today. It's a very short reading. You'll see it on Google Classroom. You have to link out to a website from NASA, do a quick reading, and then I'll have some multiple choice questions on Google Classroom. And I'm also going to go ahead and start adding once in a while a section to my lessons called Today's Cool Thing. This is something that's totally optional. It's just a fun thing that I want to do because I'm guessing that at least some of you are actually kind of bored at home all day and are not just like, jumping for joy all day long, having no physical school. So this is just a thing to check out if you're bored. It's not requirement. It's not required. It won't always relate to science. Today's cool thing is a YouTube channel. There's this guy named StyroPyro on YouTube, and his whole thing is that he loves lasers. He builds lasers, he compares lasers, he tests lasers, and so he's got these wacky, crazy videos like a homemade 40-watt laser shotgun, whatever on earth that is. I'll probably be showing him some videos from him couple lessons from now because they are relevant to what we're learning. But if you get bored after you're done with all your work today and are looking for something cool to watch on YouTube, go ahead and check out StyroPyro. He's pretty cool. Alright, that is all we got for today. You should be closing out the video and doing your exit ticket now. And hope you guys are having a great day. So long.